I didn't have those highlights in there, but what's going on is that what was that thing you're supposed to check about the powers? You really want the powers of the numerator and the denominator to be the powers of what? Of n. The powers of n. The powers of n. You want the power, overall power of the polynomial on top with respect to n to be the same on the top and the bottom, because if it isn't, you have a problem. Why? Infinity or 0, you want a definite integral, it's not 0 or infinity. Okay, so what you're looking at there is that it's pretty easy to identify what's the power of the denominator here. 2. So you're really only going to look at the things with powers of 2 in the numerator. So what I did there is I highlighted the things with powers of 2. There's the 6ab n squared right there, and then there's minus 4ab n squared right there. And then there's 2b squared n squared, and there is 2a squared n squared. Does everybody see those right there? I highlighted them. I grouped them together right here, factored out at 2n squared, and you're left with this thing right here. You see this? That thing is getting multiplied by b minus a. So I multiplied it by b minus a. The 2 and the 6 cancel, giving you a 3, which is a really good thing because you want a 3 to be in the denominator. And you're left with this right here. Look what happens. The a, b squared cancels right there. And look what you have here. You have b a squared and a squared b. Those are actually what? The same. I finished this and I was left with this. And I was like, they're not the same. They're actually the same. So what happens? They cancel. And what are you just left with? B cubed minus a cubed. The way I simplified, the way I made this process a little easier is that I just ignored. You understand the parts I ignored? I ignored all the things with just n in them. Why was I allowed to, or with no n in them? Yeah, as you take n to infinity, they become infinitesimally small and inconsequential. So I didn't pay attention to them. I only looked at the things with n squared, multiplied it out, and what was I left with? Just b cubed minus a cubed over 3. That's where it comes from. Record. So you're going down to 2, so like right here. So there it is. And you're supposed to go from what? 0 to what? 3. So you're supposed to go from 0 all the way to 1, 2, 2, 3 right here. So you're looking for this area and that. We'll call this one, let's call that one A2, and we'll call this one A1. They find the area of a triangle. 1/2 base times the height. What's A2 equal to? 1/2 base times 1/2. So that's going to be equal to 1, and this is going to be equal to 1/4. What's the answer? Negative 3/4. This is going to be negative y. Yes, it's underneath the x-axis. You're actually finding net change here. Net change. So because it's below the x-axis, it's going to be negative. That's correct. That's why. It is going to be 5 minus 0 over n times I to the 3. Like that, sure. I put in all those zeros because is it always starting at 0? No, we can clean it up just a little bit. Limit as n goes to infinity of 5 over n times the summation of I equals 1 to n of 1 plus 2 times 5i over n to the 3. You're going to then clean this up. You're then going to, as part of the cleanup, you're going to try to eliminate the what? What are you trying to eliminate? The summation symbol, right? To eliminate the summation symbol, you're going to need to know what? What's the key thing you're going to need to know in order to eliminate the summation symbols? Not the sum of cubes. Well, actually, yes, it's the sum of cubes. I'm sorry. I was looking at the wrong part. So you need to know the sum of cubes to do this one. Is that listed in your book on page right at the beginning of this section? Is there a table? Go like this. There's a table. Yes, let's find the actual page, okay? Yes. This is great. This isn't that bad. I mean, at least I don't think so. Oh, so good. I mean, it could get a lot worse. I mean, now let's multiply that 5n in right now. n times what? You get 5 plus 2 times 5 over n to the 4th power times n squared times n plus 1 squared all over 4. Be careful, right? 2 times 2. Limit as n goes to infinity of 5 plus, let's cancel that and make that a 2, So you end up with what? 5 to the 4th times n squared plus 2n plus n all over what? 2n. And that cancels, right? 2n to the 4th. Oh. 2n to the 4th. Thank you, yes. Thank you. I'm making mistakes all over the place. You guys are doing great today. So this is n squared right here. Does it still cancel? I think it still does. Yep. This goes away and this turns into a 2. So we have the limit as n goes to infinity of 5 plus 5 to the 4th n to the squared plus 2 times 5 to the 4th n plus 5 to the 4th all over what? 2n squared. To add or subtract fractions, what do we need? Common denominators. Yay. So we end up with 10n squared plus 5 to the 4th n squared plus 2 times 5 to the 4th n. Please tell me if I'm making an algebra mistake all over what? 2n squared. So what is this going to... We have to be careful here, don't we? What are we really only interested in? We're really only interested in this thing, right? In order to see this a little bit nicer, it's the limit as n goes to infinity of, let's factor out an n. What do we have here? We have 10 plus 5 to the 4th n squared plus 2 5 to the 4th n plus 5 to the 4th all over what? 2n squared. So what's this limit going to be? 10 plus 5 to the 4th all over 2. And then, what is it? 300 and what? Now here's that's a relatively, like, you know, all numbers, you need something to compare it to say that's big or small. Let's look at our original function here. We're looking at 1 plus 2x cubed. How fast does that grow? It grows pretty quickly, right? 5 cubed is 125. 125 times 2 is 200 and what? 250, right? So what does this thing roughly look like? It starts at 1, and what does it do? It goes up really quickly, right? So if you do this out, like let's just say you took this triangle right there. The base is 5 and the height is 251. What's 1/2 5 times 251? That's roughly what? It's like around what? 550 something, right? So like is it within reason that that's 317? Is that answer within the ballpark of what you think it should be? If it was like 317,000, would it be a problem?
A little bit.
Yes, but you know, what's the concavity of x cubed? What's the concavity of x cubed for x greater than 0? It's concave up. So it goes like this. So this estimate, if we do this triangle, even though it's going to cut off a little bit right here, you can pretty much guarantee our estimate by doing this triangle is going to be greater than. Even though it's going to cut off a little bit right there. It's only going to cut off a little tiny bit. So does that make sense? 317.5, is that okay? Be careful with your algebra. Be careful with your algebra. Okay. What is it? For 29. Go ahead, Bill. What? Yep. And to infinity of what? Yep. Yep. I equals 1 to n. Yep. Of what? Yep. There's something wrong. Can someone tell me what it is? Where's the 2? Where is the? It's starting at 2, right? So where should that 2 actually be? You're really close here. You're really close. Can someone tell me what it should be?
It should be
That's not specifically enough. It's not
wherever
on top. Wherever an x is. So it should be 2 plus 4i over n all over 1 plus 2 plus 4i over n to the what? 5th. There's that. Now what happens? What are the primary challenges in doing this integral?
1 is 2.
Can someone be specific? Okay, without using the word hard, can someone tell me what's one complicating thing? First of all, you would need to know what this is. I equals 1 to n of I to the 5th. Like, what does that equal? That's one thing that would be. What else is tricky?
You have division.
You do have division. Okay, that's a very good observation. There's division. It's not strictly the sum of the 5th, right? It's something over it, right? It's not that clean cut, but there's something else. algebraically, what do you have to do before you actually go out and do anything else? Yeah, you have to do this huge multiply it out, right? What part of that is going to be really annoying? The fifth 2 plus something, right? That thing is going to, right? Mainly, you're just interested in the first term, though, but still, is that kind of nasty?
Yeah.
Yeah. Okay. Can someone tell me what is the setup for 30? What's the setup for 30? Someone raise their hand. Who's going to tell me 30? Go ahead, Maddie. Yep. Guys, pay attention. Stop giggling. Yes? Yep. 1, 2 of 1 plus 9i over n. That's correct. Correct. Now, let's talk about what's specifically annoying about this one. What's hard about this one?
Got a logarithm in there.
Yeah, the ln breaks you at this point. Do you have any idea about the summation of ln, like ln 1 plus ln 2?
Clue.
Not a clue. You don't have a clue. Okay. So do we have some barriers at this point?
A little bit.
Yes. It's kind of like when you first learn how to integrate the power rule, and you're like, I can integrate anything. And then you see, like, e to the 2x or 2 to the 5x, and you're like, huh. Right? And you're like, it's equal to 5x times 2 to the 5x minus 1. No. No. So the point is you need to know what your boundaries are. And right now, you really only, think about this. You guys can integrate by hand polynomials of power 1, 2, and 3. Woo! You know, that's the beginning. Does it get more fun? Yes. Part 2 says, if f is continuous on the closed interval a to b, then the integral from a to b of f of x dx is, what does that capital F represent?
Antiderivative.
The antiderivative of f at b, evaluated at b. What kind of integral is this? This is a what? Begins with a d. When you take an antiderivative and evaluate it at a certain number, what are you getting? This is a definite integral. And if you do one definite integral minus another definite integral, what kind of answer do you get? A definite answer. So what is the definite answer going to be? Something like a number, a real number, yes. Where f is any antiderivative of f, then that is a function such that f prime capital is equal to f. Put this all together and you get the summary, which is really what you need to focus on, which is right here, which says, this is what we need to take a look at right here. The fundamental theorem of calculus. You put these two things together. It says, if g of x, suppose f is continuous. Hey, is this important? The continuity. What happens if things aren't continuous?
Things break down.
Things break down. Things can go, yay. If g of x is defined as the integral from a to b of f of t dt, then you know that the derivative of g of x is equal to f of x. And you also know that the integral from a to b is equal to the general antiderivative of f evaluated at b minus the general antiderivative evaluated at a, where f is any antiderivative of f that is a function such that f prime capital is equal to f of x. Why does it say any antiderivative? How many antiderivatives does a given function have? Many of them. There's an infinite number of them, right?
But that's only dependent on the constant.
Exactly. Exactly. And also when you subtract the constant from itself, what are you left with? Nothing. Exactly. You end up with nothing. Okay. Straight off the back.
Of x is square root of 1 plus 2 squared.
1 plus what? 1 plus what? Look at the definition, everybody. What's it? 1 plus what?
Squared.
What letter is that? What letter is that? So therefore, can someone tell me, please, what this equals? G prime of x is going to be equal to 1 plus x squared. The derivative of this function. So think about it this way. If you have a function and you integrate it and then you take the derivative, where are you?
Whack, right where you started.
Right where you started. So if you start at the square root of 1 plus t squared and you integrate with respect to x and then you go back, where are you going to be? Right where you started, but instead of t, it's going to be x. Now here's something that's interesting. You see a and b right here? What is totally missing from here? Any reference of?
A and B.
Any reference of a and b. Any reference of a and b. I think there's actually a small mistake in here. Lines. We don't know most. We like lines, right? So let's say we had the line, I don't know, y equals, let's just do this.
So
Y equals 2 plus x. Okay, we're going to have this. Stop. Yes. So let's say we had y equals 2 plus Ready? Here, ready? F of t. So f of t is, do this with the letter, f of t equals 2 plus t. Are we okay with that? So I'm going to ask you this. What does this represent? G of x is going to be the integral from 2 to x of 2 plus t dt. That represents the area under the curve from what to what? 2 to x of 2 plus t. The curve is 2 plus t. So the starting value is what? 2? So where's 2? Let's say that's right here. So this is 2. So there's the starting value. Let's actually do a specific value. What would g of 3 represent? The integral from 2 to 3 of 2 plus t dt. It's the integral from 2 to 3 of 2 plus t dt. So where's 2 to 3? 2 to 3 is right here. It's this area. That right there represents g of 3.
Oh,
You see what I'm saying?
I thought you were talking about definite.
Yes. So what happens?
Indefinite.
Indefinite. No, we're not indefinite, no. So what happens if I asked you for g of, I don't know, 5? What does that mean? That's the integral from 2 to 5 of, in this case, f of t, which is the same function. What's that going to be? 2 to, it's going to be from here all the way up to 2, 3, 4, and 5. It goes all the way up to here. So this right here represents g of what? 5. I have a question for you. What happens if I ask you for this? G of, and I'll change colors. What happens if I asked you for, let's say, g of negative 1? What does that represent? The integral from 2 to negative 1 of what? F of t dt. It's the same function. Is that going to be positive or negative? You're going from 2 all the way to what? Negative 1. So you're looking at this. The area is above the x-axis, but what direction are you integrating? You're integrating from right to left. Now, do you remember there was something from last week? What can you do with the limits of integration? You can flip them, but if you flip them, what do you do? Change the sign. G of negative 1 is going to be equal to negative, you don't change the sign, it's negative of negative 1 to 2 of f of t dt. Well, you know that the area under the curve from negative 1 to 2 is positive, so therefore when you multiply by a negative, the whole thing becomes negative. So this function, g of x, is just changing where that x is going to. Does it make sense now?
Yeah.
Okay, good. Kind of annoying. You have to do a lot of what?
Calculus that you don't.
No, it's not the calculus. I highly doubt that you guys are making a mistake on the calculus of the Riemann sums. It's the algebra. There's a lot of algebra involved. What does the fundamental theorem of calculus tell us on this? If we're defining g of x to be the integral from 0 to x of t squared dt, what do we know? We know that g prime of x is equal to what? In this case, it's going to be x squared, correct? That's the first thing it tells us. X squared is continuous everywhere, especially on that closed interval. Okay, so now the fundamental theorem of calculus part 2 tells us that this equals to, so we know that the integral from 0 to 1 of x squared dx is going to be what?
Big F. So antiderivative.
Big F of 1 minus big F of 0. In this case, f of x is equal to what? No. What is f of x? No. What is the general antiderivative? It is x cubed over 3 plus what? C. So what is f of 1? Plus c. What's f of 0? Plus c. So this tells us that this is equal to 1/3 plus c minus what? C. So that's equal to what? 1/3. Is that a slightly little bit, tiny bit less algebra than what you've done before? Yes. The reason we're allowed to do this is because of the fundamental theorem of calculus part 2, which tells us that this equals the difference of the general antiderivative evaluated at 1 minus the antiderivative evaluated at 0. The upper and lower bounds, yeah. It says evaluate that integral from 3 to 6, 1 over x, and this is something we wouldn't be able to do with a Riemann sum. We have to use the fundamental theorem of calculus part 2. So we get to this, right? We get to that. So in this case, we have to find the general antiderivative of 1 over x.
ln.
In this case, f of x is going to be equal to what? ln of what?
X.
ln of x. Now, just to start doing this out of
Absolute
practice, absolute value it. Let's just say I'm going to summarize it right now. We're going to keep it. We'll revisit this many times, but by absolute valuating it, you eliminate many of the problems that you could be dealing with. Okay, because what can't you do? You can't do the natural log of
Negative.
a negative number. Just be very careful. It doesn't really come into play at this time because what are we evaluating from? We're okay for now, but it is that. So if we do this, what is this going to be equal to? This is going to be the ln of, what is this equal? 6 minus what?
ln.
3. Does that simplify to anything nice? Yep. ln of what? Oh, please, come on. You have 5 seconds to tell me what the answer is. 5, 4. Thank you. Bill saved you. Yes, when you subtract ln A minus ln of B, it equals what? A over B. Do you remember that, everybody? You do not. Remember this? What can you do with the coefficient of something? It's also equal to plus ln of B to the negative. Remember, you can take it and bring it to the top. You remember that? And what do you do with plus? Multiply. And what's A times B to the negative 1? A over B. Another way to think about it. It's another way to think about it. Okay, let's pause this a second.
Interval A to B closed.
Exactly. That's the thing. It's not continuous on the closed interval. You're absolutely right. That's why you can't apply the fundamental theorem of calculus. What about this, though? What happens if I asked you for the integral from, I don't know, -3 to 3 of 1 over x dx? This is very similar. Is there an asymptote?
Yeah.
Yes, but what does this graph look like? It looks similar, but what's the difference? No, well, no, it has there's this, and then what else is there? There's this, right? So if you go from -3 to 3, what do you think the integral should be?
It's 0.
Yeah, because it's theoretically like doing the exact same thing on both sides, right?
Cancel out.
Correct? But here's the thing. Let's just do this out like with bad calculus, okay? This is actually not something I should be doing with you, but let's do bad calculus. What's the integral of 1 over x? Natural log of x. So let's do the natural log. Let's just natural log of x of, let's just say we did this really quickly. Natural of x from what to what? -3 to what?
3.
So first of all, you're doing the ln of 3 minus ln of,
Negative 3.
and that breaks because this is not defined, and you're like, sad face, right? You're all of a sudden sad face. Now, you could say it is the natural log of the absolute value, and it's -3 to 3, in which case, what do you get? ln 3 minus ln 3 is 0. So sometimes you get answers that make sense, but just be really careful. It's not always going to be like that. Be really, really careful. Here's the other thing. This is nicely symmetric, right? This is an odd function. Is the function always going to be odd?
No.
Could it be steeper over here than it is over here?
Yep.
It is possible for the steepness to be different on different sides. It could approach differently, right? Things get weird, right? Things can go to infinity at different speeds, right? Infinity minus infinity. Remember indefinite integrals with L'Hopital's rule, like 0 over 0? Does 0 over 0 always go to 1?
No.
No. Does infinity over infinity always go to 1?
No.
No. That's why we have things like L'Hopital's rule to tell us that. Okay, so just be careful. Let me write that down and put it on the record. Be careful. For the most part, though, is this going to be? Is this the payoff for you?
Yes.
Yes, because what does this allow you not to have to use? Yes, basically. What was the topic we just did? What's it called? Begins with an R.
Riemann summation.
It allows you to not have to use Riemann
We
summation.
don't
Will
go
you
through
have
all
to?
that work.
You don't have to go through all that work. Exactly. I mean, look at look what we did right here. What did we do for this one? This first one we did right here.
A lot less than we had to.
Yeah, for the first one right here, like, ooh, goes to x squared. It's 1/3. You're done, right? Like, this was the work you had to do. Is that a lot less than what you did before?
Yeah.
That's a heck of a lot less than what you had to do
It's
before.